Hello everyone. Welcome to another online lecture in distributed networks. In today's lesson, we are going to be looking at spanning tree protocol. So, in the previous weeks, we have covered a number of topics relevant to expanding networks, relevant to building up networks into larger organizational environments, larger deployment environments, and continuing from that, today we are going to be focusing on the topic called spanning tree protocol. So, one of the things that we have discussed previously, particularly in terms of switch networks, is that having redundant pathways is a good idea. So, there are many reasons why we may want to have redundant pathways, and one of the main reasons is to eliminate a single point of failure. So, for example, in the network that is shown in this diagram, uh, what we can see here is uh, say from the switch 2 to reach to say PC4 or this particular device, what we have is we have a couple of different pathways. We can go through a direct pathway like going to S1 and then going to the device, or we can go to S3 and then S1 and then onto the device. So the traffic is originating from PC1. So what happens is, what we can see here in this example is there are two possible pathways to reach the same destination. So one pathway is this and the other pathway is this. So now what happens is, when we have such redundant pathways, it can also lead to some problems. It can also lead to some problems in terms of what we call as loops. So for example, what may happen is, say if something originates from here, it can go in a loop like this through the same sort of switches. So that is one of the things that we are trying to eliminate when we are having such redundant links in our network. So when we are talking about layer 2 loop issues, there are three main loop issues that we can identify. The first one is what we call as MAC address, MAC database instability. So what happens is, say for example, when a switch learns about a MAC address. So for example, when PC1 attaches to S2, it will learn about the MAC address for that particular device, and then it will build its MAC database. Then it will on forward that information to other switches. So then this can go to that switch. So then S3 will update that. Then it will forward that to S1. So now S1 will update that. Now S1 will send it again to all the switches. So it will be received again back at S2. So now what happens is, S2 has received the MAC address for PC1 twice. So that is what we call as MAC database instability. The copies of the same information is being received at the same switch at different times. Then what that can lead is, for example, S2 would initially be of the opinion that it can connect to PC1 through this particular port. But now it will update saying now it can connect to PC1 through this particular port. So what happens is, even though fast Ethernet 11 is the best port to connect to PC1 because it is directly connected, it may still choose the other one because that frame was received later, that update was received later. So that is something that we would want to avoid in our networks. Then another one is what is called as broadcast storms. So broadcast storms is basically when broadcast packets, broadcast frames are being sent on the network, they are going to be stuck in this endless loop, or they are going to be continuously being propagated in our network. So because of this loop is there, they will keep on being sent again and again by each of the devices. So for example, if S1 receives, it will send a broadcast. Then when that is received at S2, it will send again a broadcast. That will again reach back S1, so it will be in that continuous loop of broadcast packets, broadcast frames. So it will be endlessly flooding the network. Then the other issue that we will identify is what is called multiple frame transmission. So again, what can happen is, even if it is a unicast frame, it can again be delivered to the same destination multiple times. For example, if a frame needs to be sent to say that is the destination, it may send couple of different ways. So again, we may receive multiple copies of the same frame. Destination is the same, origin point is the same, but multiple copies are being received because of this layer 2 loops. So this is something that we would want to avoid when we are building larger switched networks, especially when we are building them with redundant links that can lead to having these loops. So as we said earlier, when we think about MAC address instability, so what we are learning here is, say if we think about this particular network that is shown in this diagram, what we can observe is the MAC address table at this point at the initial stage is fairly what we as we expect. So for PC1, S2, this is the best port to connect. For S3, this is the best port to connect, and S1, this is the best port to connect. So that is perfectly all right. But now when this information is exchanged, so when this information is exchanged between the switches, because they will exchange their MAC address databases. So when that is exchanged, now they have updated their information with something that is not the best option there. So for S3, the best way to go is not through this. That is not the best way, because that is not the shortest path, for example. Similarly, this is not the best way for the other one either. So that is what we mean by MAC database instability. And the other main issue is this can keep on happening, because with layer 2 frames, there is no concept of a expiry or a time to live. So what can happen is they can keep on propagating endlessly. So they can go back and forth between these switches continuously, leading to this MAC database being updated continuously. So it will, whenever new information is received, updated, again updated. So it can keep on going like that. So that is one of the main things that we need to avoid. Then broadcast storms is, it's fairly simple, and one of the main issues that can happen is it can lead to sort of denial of service attacks, because the network resources are being inundated with these unnecessary broadcast frames, and it can take down the network in a very short period of time. Say for example, if a broadcast frame is being sent from a particular device, and then if it is going to loop in this in between these switches, now it is going to generate more and more frames, because it is going to exponentially increase as uh, a copy is generated each time it is being received at a switch, and it is again sent back to all the switches. So it is going to inundate the network, and after a point in time, very quickly the network is going to go down. So that is again something that we need to avoid, that is broadcast storms. Then when we think about duplicate unicast frames, if we look at the diagram that is shown here, so PC1 needs to send a frame to PC4. So that is what we need to do. But at switch 2, we don't have the MAC address for PC4. So what would happen is, because the MAC address is not there, MAC address is not available, what it would do is it would send it as a broadcast frame. It would send it as a broadcast frame to all the connected switches. So it will send to both of these switches. So now the switch 1 here has the information in its MAC address data. In its MAC table, it has the information for that particular device. So it can forward that onto the device directly. So that can happen. But then again, if we think about switch 3, for example, switch 3 does not have the particular MAC address for that particular device. So again, it will send broadcast frames again, and what would happen is another copy of the frame is going to be received through this. So what can happen is, we can continuously multiple copies of the same frame will be received at different times or with time differences. So we are going to receive duplicate unicast frames. So that is also a problem that we may have to avoid when we are building these networks with redundancies. So to address these problems, the spanning tree protocol or the spanning tree algorithm is used. And the main idea behind the spanning tree protocol is that when we have redundant links, we will make sure that one of those links are disabled at any point in time. Say, for example, if we take this network, so our problem was we had these two redundant pathways. So this was one pathway and this was the other pathway. So then what we would do is we would disable one of these when it is not needed. And then, for example, if this link goes down, if that link is offline, then we may use the other redundant link. So we will still get the advantage of having the redundancy. So the failures are addressed to it addresses the failures, but it is not going to create those loops. So in normal operation situation, only one of the links will be active, other one will be inactive. And when the active link, for example, goes down for a particular reason, then the inactive link would come active again. So that is the main idea behind the spanning tree protocol. So when we think about spanning tree protocol, we can identify a number of ports, a number of categories of ports within our switches. So these categories of ports will depend on the particular spanning tree algorithm that we are using. So the basic spanning tree protocol will have mainly 3 ports. One is what is called the root bridge. So root bridge is the device that we are selecting as the main main switch device on the switch network. So we will select that as the root bridge. So that is one of the devices will be elected or selected as the root bridge. Then from other devices, from other switches, the port that will lead to the root bridge, for example from S2, this is the port that will lead to the root bridge. From S3, this is the port that will lead to the root bridge. So the port that will lead to the root bridge with the lowest cost will be identified as the root port. Then the designated port is the port per link, so per segment, and it is the one that can get you to the root bridge with the lowest cost. For example, for this link, that is the designated port. For this link, that is the designated port, and here this is the designated port. Then in addition to these, in what we call as the STP protocol, we will look at that a bit later, there are two additional ports. One is called the alternative port, which is the backup port for the designated port when the other side is not the root port. So for example, in this link, this is not the root port, so the other one is the alternate port. And then in STP, there is also what is called the backup port, which is the backup for the root port. Again, we will look at this a bit later. So now let's look at how the root bridge will be selected. So when there are a number of switches in the network, one of those switches will have to elect to become the root bridge, or will have to be selected to be the root bridge. And this will happen in the STP, or the spanning tree protocol. This will happen using what is called the lowest bridge ID. So the bridge ID is a combination of a bridge priority number, which will normally default to 32,768, which can be changed as well, and the lowest MAC address, or the MAC address of the device. So the combination of the MAC address of the device and the bridge priority is the bridge ID, and normally the lowest bridge ID will depend on, because the bridge priority is normally set to default, it will depend on the lowest MAC address to become the root bridge. So the device with the lowest MAC address will be elected as the root bridge. So that will be the first thing that will happen when the spanning tree protocol operates. Once the root bridge is elected, once we know the root bridge is there, then we will have to calculate the root path cost, or the cost to reach the root through number of different redundant paths. Say for example, if we take S2 for example, there are two ways that we can reach the root bridge, through trunk 1 or through trunk 2 and 3. So here, for each of these paths, the cost can be independently calculated, and the cost is normally associated or calculated using the speed of the link. Link speed is one of the factors that can be used to calculate the root path cost. Additionally, this can also be manually configured for the interface by modifying using the spanning tree cost command. So we can let it be calculated using the standard link speeds, or we can manually specify a particular path cost for a particular path. So now based on this particular root path cost can be calculated to all the paths that we have from a particular switch to the root bridge. So once when we think about the spanning tree protocol, we will also have what is called the bridge protocol data unit. So this is like the information packet that will be sent, or the information frame that will be sent between when we are operating on this protocol. So it would have a number of information identifying the routes, the bridges, the port IDs, and all these different information relevant to this particular protocol will be shared through this. So when we think about the actual operation of the protocol, these data units, these bridge protocol data units will be propagated across the switches in a particular order. So when a switch is powered on, so it will first assume that it is the root bridge until other BPDUs are sent and spanning tree protocol calculations are performed. It will first initially assume that it is the root. It is the root bridge. So when switch 2 is switched on, what will happen is it will generate, it will initially identify itself as the root ID and the bridge ID, and it will send that information across in a frame, in a BPDU frame. So that will be received by S3, and S3 will compare the already available root ID information and the newly received information and see which is the largest. If the received one is the largest, that will be assigned as the root. Otherwise, S3 will still keep itself as the root. So if S2 is lower, S3 will update and it will update its information. If not, it will not update. Then S1 will receive the same information as well from S2 because it is also connected, and there S1 has the lowest BID. So S1 has the lowest BID. So S1 knows that it is the root, whereas S3 thinks S2 is the root bridge, so it will send that information out to S2 and S1. So when the information is received back at S2 from S3, because S3 has also assumed S2 is the root bridge, so it is also sending back saying S2 is the root bridge, so S2 still thinks it is the root bridge. And S1 is also receiving that information from S3 saying S2 is the root bridge. But S1 knows that S2 is not the root bridge because it has the lowest BID. So it will ignore that information. And now S1 will send out a BPDU, and that will contain the information saying S1 is the root bridge. Now once that information is received at S3 and S2, they will compare the BIDs with their BIDs. So S3 thought S2 is the root bridge, S2 is also thinking S2 is the root bridge, but when compared to S1, S1 is the lowest. So now all of them will update S1 as the root bridge. So that is the basic idea of how a root bridge will be elected. Say for example, a new switch comes along online, it will send out the information saying I am the root bridge. Then the other ones will compare and see if they are the root bridge or the one that is claiming is the lowest BID. If the one that is claiming is the lowest, they will update themselves. If not, they are the lowest, they will send that information out. After this information goes through the network for a while, like goes through all the switches, at some point it will come to the convergence saying a particular switch is the root bridge which has the lowest BID, and the others will update themselves to saying that is the root bridge. So that is the basic idea behind the BPDU propagation process. And by default, the bridge priority is normally set to a default value. Hence, the MAC address or the lowest MAC address becomes the determiner of the lowest BID. We can additionally change the priority value to something else to influence the root bridge election. For example, if we go and change the priority value for S2 to a lower value than S1, now what we can have is S2 becoming the root bridge, even though it doesn't have the lowest MAC address. S1 has the lowest MAC address, but we can change the priority ID differently and make a different switch as the root bridge. Now let's look at some of the different types of spanning tree protocols. There are a number of spanning tree protocols that has come about over the years. Some of these are open protocols and some of these are proprietary protocols. For example, PVST plus or Rapid PVST plus, these are Cisco proprietary protocols, whereas 8021D, 8021W, these are open protocols, open standard protocols. But largely, the fundamental idea behind these protocols still remain the same. There are a number of differences between these protocols as well. Say, for example, the resource requirement is significantly different between these protocols. For example, when we go through the latest protocols, some of them require very high resources for processing needs, but at the same time, they can also reach convergence. So that is identifying the root bridge very quickly. So they are able to identify that convergence very quickly. And one of the important factors could be their ability to support VLANs. For example, like, do they support all VLANs, or do they have to be configured or managed for a per VLAN basis? So there are some differences in that sense as well. But the basic idea of spanning tree protocols will still remain same across all these different spanning tree protocols. Let's briefly look at the PVST plus protocol, for example. So the original 8021D protocol, the common spanning tree protocol, it doesn't consider a number of things like load sharing, because even though we have these redundant links, it will readily disable one link and it will block all other links. So what can happen is it can reduce the efficiency of the network, because it is not utilizing the link at all, because it is altogether blocking that link for all VLANs. But because it's a fairly simple protocol, it doesn't need a lot of resources. The devices can be very low powered, low processing power is required in such devices. Whereas the Cisco PVST protocol, what it has is a spanning tree instance, a spanning tree for each of the VLANs separately. So for each VLAN, a port can be blocked and another port can be enabled. For example, what we will have is, for a particular VLAN, this port will be blocked, and another VLAN, this port will be blocked. And for different VLANs, there can be different root bridges as well. So for a particular VLAN, there could be one route, and another VLAN, there could be different route, because VLANs may be constructed differently. And one of the sort of differences or disadvantages is, because it has this amount of calculation in a per VLAN basis, it may require a fairly high amount of CPU resources to do all these computations. But that is the main difference. In the original 8021.1d, it is a overall for all the VLANs, it has the same blocking of trunks, whereas in Cisco PVST Plus, it has a per VLAN based spanning tree. In addition to that, in PVST Plus, we can also have what is called the bridge ID and the extended system ID, the bridge priority ID, and will be based on the bridge priority and the extended system ID. And one of the things that can be done for this is the VLAN number can be used as that as part of that priority value. So then that will dictate the different priorities based on the VLAN numbers. And based on specifying these things in a manual manner, like for custom for different networks, we can select different switches as root bridges based on the type of traffic requirement, and that may be necessary. For example, in certain network arrangements, the most of the devices of that network will be connected to a particular switch, and having that as the root bridge would be an ideal way to connect rather than having another root bridge. So we can have different root bridges for different VLANs based on the traffic arrangement that they have. And sometimes it can also be some of the devices can be more highly powered, have more CPU processing capability. So again, they may be able to handle more traffic, more processing happening in them. So for a number of reasons, we may want to select some of the switches as roots and some as not as roots. They will send or they will elect the other ones as roots. By the way, we specify the priorities and the extended system IDs and so on. One of the important protocols when we think about STP or spanning tree protocol is the RSTP or the Rapid Spanning Tree Protocol. So a key issue with STP is it takes a lot of time to reach convergence. It takes a lot of time to get to the point of understanding what is the root bridge and updating it across all the switches in the network. So in a typical network, it can take up to like half a minute to 1 minute even. So with rapid spanning tree protocols, the main issue it addresses is this convergence or the delay in convergence. So what happens is in rapid spanning tree protocol, the BPDUs or the data units that are sent to propagate this information, they are normally sent in STP. They are normally sent as a way when it is triggered by a root. So, for example, a new device attaches and then it sees itself as the root, then it will send that information. So, or if a new update is received, then it will send that information across the network. Whereas on in RSTP, the bridges can they don't have to wait until a new link is inactive before propagating this new information. So they will keep on sending out this information in a frequent manner, so they can quickly reach the convergence because this information is already being propagated across the network. And one of the things that we will have in RSTP, as we early identified, is two additional port designation. One is called the alternate port or the backup root port, and a backup port which is the backup for the designated port. So at all times, all the switches will have a root bridge and also a backup port. So a root port and a backup port. So if one link fails, it can switch back to the other one and still try to keep on functioning within the same arrangement. So that is the main difference in RSTP. So it can lead to convergence much quickly than in the simple STP protocol. The main difference in RSTP is because it has a backup for the root port. So if a particular link fails, then it will always have the backup port. So that root port is no longer working. So it will choose the next backup port that is available and choose that as the link that it is going to communicate through the root bridge. So it will always have this backup port that can lead to as a backup to the root port. And similarly, for all the destination ports, again, there are backups. So again, they can quickly readjust or rapidly reset when a link is failed. So if this link fails, it can quickly reset and go through the other alternate link. So that is the main difference that we get from a RSTP or the Rapid Spanning Tree Protocol. And when we consider the BPDUs that are sent in RSTP, again, here we have a main difference here. That is, it has a number of additional flags and additional information in some of those BPDUs. But in addition to that, BPDUs are used as a mechanism of a keep alive mechanism. So that is, they will expect BPDUs to be received or sent and received in a particular order continuously, and if they are missed or if their reception is missed for 3 consecutive packets or consecutive frames, then that link will be assumed as a loss of connectivity. So the fact of sending BPDUs continuously, one, it will continuously update the information even before so it will always have this up-to-date information propagated. So that is one aspect. The other aspect is that continuous sending of this information will also be used as an indicator to see if a connectivity is still active or not. And if a connectivity is lost, it will be gauged using this mechanism of keep alive, and then it can switch to an alternative link, as we mentioned previously. Then when we think about the states of ports in the different between STP and RSTP, in STP we have a number of states: disabled, blocking, listening, learning, and forwarding. So it has to go through all of these states from disabled to forwarding. It has to go through a number of stages to reach that point. Whereas in RSTP, it has only 3 main states. So it will go from discarding, learning, and forwarding. So they are the 3 ports that it will operate in. Then from the Cisco side of things, from a proprietary version of the protocol, it has the Rapid PVST protocol, a Rapid PVST Plus protocol. So it is again fairly similar to how PVST and STP were similar. Rapid PVST is similar to RSTP. Then one of the other things that we can do when we are configuring these spanning tree protocols is identifying edge ports. So edge ports are the ports that are normally connecting to end devices, not switches. So these are not connecting to switches. These ports are connecting to other edge devices like a computer or something else. So there's no need for any spanning tree protocol information to be sent to these ports. So because these ports doesn't have to be considered when we are considering a spanning tree protocol. So only the ports that are interconnecting the switches will have to be considered for this purpose. So we can eliminate them from our spanning tree calculations, eliminate the edge ports from our spanning tree calculations. Then in terms of links in a switch network, again we can identify a few different types of links. One is what we call as a point-to-point link. So a point-to-point link is where the switch or the devices at both ends are functioning in a full duplex mode. So they are functioning in a full duplex mode. So they can send and receive information from both ends at the same time. Whereas we may also have what is called sometimes shared links that may go through, say, for example, a hub, for example. They may connect in what is called a half duplex mode. So the information can only be sent and received in one direction at a particular point in time. So we may encounter these different types of links as well. Now let's briefly look at configuring the spanning tree protocols in a switch environment. So one of the main things that we will configure is about influencing the root bridge selection. So if we are, for example, we are configuring it for a particular VLAN, and we can specify a particular switch as whether it needs to be the root, whether it needs to be, so we can set a priority value there. So we can either set it as primary using a primary or a secondary command, or we can set it using a priority value. And once we do that, we can use the show spanning tree command to verify that. So we will go into the switch configuration, so to a particular switch configuration, and we can specify that. Then, as we said, if you want to have some of the end devices, the ports that are connected to end devices, we can go into those interfaces. So we can, for example, here F011 is connecting to an end device. So we can go to the interface to fast Ethernet 11, and we can specify that as spanning tree port fast. So then it will not be configured, or it will not be considered as part of the spanning tree calculations. It will be considered an end device. Then we can also configure, another thing that we can configure is when we are considering PVST plus, how we can configure load balancing. So here the main thing that we do here is configuring both a primary and a secondary there. So for example, switch 3 can be configured as a primary for VLAN 20 and secondary for VLAN 10. On the other hand, switch 1 can be configured as primary for VLAN 10 and secondary for VLAN 20. So based on, or we can even configure them using priority values that we are giving as individual numbers. We can configure them as priority values there. Another thing that we can configure is actually configuring the specific spanning tree protocol mode that is used in a device. So, for example, we can go into a switch configuration and specify what is the spanning tree protocol that we are going to use, whether we want to use rapid PVST or whether we want to use something else. We can configure, and additionally we can also configure the specific link type. So by going into a particular interface, we can specify whether it is a point-to-point link or so on. We can specify those as well. Now then, when we look at some of the common issues that we can encounter in STP configurations, so as with any sort of switch router configurations, the best thing that we can always do is using the show command to see whether the configurations are done properly and the information or the propagation of information has gone through properly. So if the root bridge is elected properly and that information is passed on through all the devices, so that is something that we would try to ensure that that has been done. So we can use two things. One is we can use the show spanning tree information to see, and also we can also use the spanning tree command with a particular VLAN. So we can specify the VLAN and verify whether the interfaces are communicated correctly and the port designations are associated correctly as well. One of the things that we have to be mindful is we should not be turning off STP in a particular switch without having a serious think about it. So that is because of the lack of a TTL mechanism. When something is switched off, that information propagation may not happen as expected. So then that can lead to undesirable consequences within the network. So that is something that we may want to avoid, and that's why we would not want STP to be turned off without having a proper thought about that. One of the things that we can do is we can manually remove the redundant link. So we can manually unplug or through configuration disabling the link, and then let the spanning tree calculations to be done again, and then we can reconnect and see if things are working properly. So that is something that we may do at some points as well. And one of the other things that we would do is when we have a stack of switches, so when we have switches that are interconnected to each other as a stack of switches, we may want to consider all of them as a single unit in a spanning tree protocol. For example, we may not want to take this as a distance, an administrative distance when we are calculating port distances and so on. So we may want to configure these as a single switch, a stack as a single switch. So we may have to configure those accordingly as well. So in summary, the main idea behind spanning tree protocols is when we establish these networks, when we establish these switch networks with redundant pathways, they are going to create these loops or unnecessary loops that are going to create some problems like MAC database flooding, and so on. So one of the ways that we avoid this is by disabling some of these links at a particular point in time and then utilizing them at a later point in time. So that is the spanning tree protocol. And there are a number of variations, proprietary and open variations like PBST plus, rapid STP. So there are a number of variations for these spanning tree protocols. But the basic idea still remains the same. When we have redundant links, we want to avoid the looping of frames. So that's all we have to discuss on spanning tree protocols. There will be a number of other resources shared along with this material that you can refer to get a bit more understanding of each of these protocols. And other than that, if you have any question, always reach out to me through your usual communication channels. And until next time, thanks for joining in this lesson. See you and bye.